Hi everyone. So today the topic of our discussion is a very important and a basic concept of conservation of linear momentum. So in this particular interaction, we are going to discuss some advanced level problems and multiple methods for doing the same problems based on this topic, right? So before going to the discussion of the problems, let us first try to recollect that what was this conservation of linear momentum exactly, right? So according to this principle, if the external force acting on the system is zero, which means there is no external force acting on the system, then in that case, the linear momentum of the system will remain constant or conserved, which means you can simply say that whatever finally you are going to get the linear momentum of the system, that has to be equal to the initial momentum of the system. So whenever we say that the final physical vector quantity will be equal to the initial vector physical quantity, that is the linear momentum, which means they should be equal in terms of magnitude as well as in terms of direction, right? So it is a very fundamental thing. Fine, but we have already proven it earlier, right? So no need to prove it again and again, right? We already know that. But yes, while implementing this fundamental concept, we must be making note of two important things, which means there are two fundamental questions one should be asked himself or herself before implementing this principle, right? So what are these two things? The first one is, see, whenever we are saying that external force acting on the system, so one must think what should be the choice of system. The system should be chosen in such a way that maximum number of forces, or you can simply say all the forces, will become an internal factor. All the forces will become internal so that there will be no external force acting on the system. And only in such case, when there is no external force acting on the system, then only the linear momentum of the system can be conserved. Which means the first thing you should be make note of is choice of system. Choice of system. The system should be chosen wisely, right? And the second thing is choice of frame of reference. Choice of frame of reference. Now what is that, sir? We have already applied choice of frame of reference, FOR. We have already applied this conservation of linear momentum numerous times since class 9th, right? But we never thought of this frame of reference. Now why that is so important, right? See, whenever you are saying that the final momentum of the system will be equal to initial momentum of system, there are two mistakes which can be there, right? The first thing is, while writing the final and initial momentum of the system, you are standing at two different places, which means you as an observer are having two different states of motion while writing the initial and final momentum separately. This must not be the case, which means while writing the initial and final momentum of the system, one should be consistent, one should be having a fixed frame of reference. So this frame of reference must be fixed. You must be consistent with that frame of reference. Not only this, not only the case of initial and final. See, whenever you are talking about a system, a particular system, we already know that a given system will be comprising of many small bodies or parts, right? So while writing the momentum of the system, we must be writing the momenta of the individual objects. Now, when we are writing the individual linear momentums, then also our frame of reference must be fixed, which means we need to observe all the individual particles and we should write their linear momenta while standing at one particular position only, or you can say with respect to only one frame of reference. Now let us analyze or let us understand that why these two important factors are to be taken care of. We are going to discuss one small problem based on this, right? Problem number one. Initially, system is at rest. The examiner is telling you that initially system is at rest. See, whenever we say that system is at rest, I'm not saying that velocity of center of mass will be equal to 0 and there can be individual particles, few of them can be moving in the positive direction, the rest of them can move in the negative direction and they will nullify the velocity of center of mass. No. Whenever I say that system is at rest, which means velocity of center of mass is by default 0, rather individual particles, not even a single particle of the system is actually moving. Which means each and every particle of the system must be at rest. The meaning of system is at rest is each and every particle of the system must be at rest. Fine. So initially system is at rest. You need to find the recoil velocity. You need to find the recoil velocity of the plank when man starts walking over it. There is a man standing over the plank which was initially at rest, and now the man starts walking over the plank. So there will be a recoil velocity attained by the plank. You need to determine it. Let us try to understand the situation diagrammatically. It is already mentioned in the problem. Now there is a smooth horizontal surface. There is a smooth horizontal surface over which a plank of mass capital M is kept. Plank of mass capital M is kept initially at rest, and a man is standing over one side of the plank, and the man is having a mass m0. It was also initially at rest. Now the man starts walking over the plank with a velocity u, but this velocity u is given with respect to plank, which means if plank is considered as an observer, then according to the plank, the man will be walking over the plank in the forward direction with a velocity u. Got the point? And you need to determine the recoil velocity of the plank. Got it? Now, we are going to solve this problem by applying the simple principle of conservation of linear momentum. But before the application of this fundamental principle, we must be thinking the very first part, what should be the choice of our system? Now here, the choice of system or the system must contain man having mass m0 plus plank having mass capital M. Now why that is so, sir? Why that is required? That is required due to a very, very basic reason. See, if the man wants to walk over the plank, can I say the contact surface of man and plank will be smooth? No, obviously not. Because on a smooth surface, even if we try walking, can we walk further? Can we walk forward? No, because there is no friction in order to support our motion. One must need, we as humans, if we want to walk forward, definitely we want friction in order to support our motion. Without friction on a greased surface, on a smooth surface, we cannot walk, we cannot change our position. Fine. So, understanding this situation, can I say that let us maintain some gap in between the plank and the man in order to have a better understanding of the topic. So if the man wants to move forward with a velocity u, anyways with respect to plank or with respect to ground, it hardly matters. What will be the direction of friction? The first thing is the contact surface must be rough. The contact surface must be rough. Let's say the coming friction force will be Fr. Now what should be the direction of friction acting on the feet of this man? So if we want to move forward, the friction is going to support our motion, which means definitely the friction will be acting in the forward direction. Fine. And where will be the direction of friction acting on the plank? The direction of friction will be in the backwards direction. Because of this friction, due to this direction of friction, the plank is going to attain a velocity in the left direction, which means backward, or you can say this left direction. Fine. But see, if we are going to take man as a system, can we conserve its momentum? No, because this friction is going to behave as an external force. If we are going to take plank as a system, can we conserve its momentum? Again, no, because this friction is again going to behave as external force and it is going to change the state of motion of the plank in the backward direction, which is actually happening. Fine. But yes, if we take man plus Planck as a system, then in that case, the friction force coming into the picture will become an internal force. That is going to become an internal force. This will be an internal one. So what is the external force acting on the man plus Planck system in the horizontal direction? There is nothing. Which means, can we say external force acting on the system, the man plus Planck system in the horizontal direction, that is 0. There is no external force acting on the system. In that case, we can simply say that momentum of the man plus Planck system in the horizontal direction is going to be constant. It will be constant. Fine. And if it is constant, can we also write final momentum of the system in the horizontal direction? It must be a vector quantity, right? That has to be equal to initial momentum of the system in horizontal direction. But what is the initial momentum of the system? It is 0. Why? Because in the problem, the very first statement is initially the system is at rest. And if the system is at rest, can we say the initial momentum is going to become 0? It will be definitely 0. So if initial momentum is 0, the final momentum must be equal to 0. So what will be the momentum statement? Can we say mass of man, that is m0, into velocity of man with respect to ground plus mass of Planck, capital M, into velocity of Planck with respect to ground. These are the final velocities, and that is equal to initial momentum, that is nothing but equal to 0. Fine. Do we know the velocity of man with respect to ground? No, we don't know, as the velocity of man is provided with respect to Planck and not with respect to ground. Similarly, do we know the velocity of Planck with respect to ground? No, we don't know. Rather, we need to determine it. That you need to determine the recoil velocity. It is quite understood that recoil velocity is to be obtained with what frame of reference? Our frame of reference must be ground. So the second thing is, we need to choose our frame of reference for this statement. That should be ground. And we need to be consistent about it. Which means while solving this particular problem, we are not going to change our frame of reference. Is that understood? Right. So let's say that velocity of Planck with respect to ground is minus v0. Now why there is a negative sign? Why there is minus sign? Because in class we are taking the convention that forward direction will be positive, backward direction will be negative, or you can say left will be negative. So that's quite understood by this free body diagram of man plus Planck system in the horizontal sense. The direction of velocity attained by the Planck must be towards the left, right? So let us say that it is v0. Understood? Which means velocity of Planck with respect to ground for this statement will be minus v0. Then can we write according to relative velocity that velocity of man with respect to ground can be analyzed as velocity of man with respect to Planck plus velocity of Planck with respect to ground. In this way we can obtain it, right? So what is the velocity of man with respect to Planck? Sir, it should be plus u. Why plus? Because it is moving in the forward direction. Right? So we are going to consider this direction and this speed. So what will be velocity? It is plus u. Plus, what is velocity of Planck with respect to ground? Minus v0. So what is that? U minus v0. So I'm highlighting this equation. According to this equation, can we say m0 into velocity of man with respect to ground, that is u minus v0, plus capital M into minus v0, that must be equal to 0, initial momentum. What is our motto? What we need to determine? Do remember it, right? We need to determine the value of v0. Then in that case, can we simplify it this way? m0 u minus m0 v0 minus mv0, that must be equal to 0. So you can shift these v0 terms over that side, so they both of them will become positive. So you will get the value of v0 as m0 u over m0 plus capital M. m0 u over m0 plus capital M, and velocity of Planck with respect to ground, that will be equal to minus V naught. So that will be equal to minus of m naught u over m naught plus capital M. Is it fine? Easy problem? So it seems to be a very simple problem based on conservation of linear momentum, but there can be mistakes if we don't take care of two things. The first thing should be choice of system, right? And the second thing is we need to be consistent regarding the choice of frame of reference as well, right? The story is not yet completed, as I have already told you many times that, can you say that this is a two-particle system? Right? Man plus Planck. And I have already told you numerous times that this two-particle system is one of the very common and important systems in physics as far as 11th and 12th grade are considered. Fine. So I'm gonna give you a very simple and analytical shortcut for this. And every time I tell you that there is nothing like shortcut, everything is a generalized solution. And with every generalized solution, we must be remembering the constraints associated with that particular solution. So what is that constraint? This shortcut is applicable only for two-particle system, first thing. That too, when this two-particle system is initially at rest. This two-particle system is initially at rest. Fine. So what we can say, see here, the first thing which we can say is that initially if it has rest, the system is at rest, which means both the particles of the two-particle system must be at individual rest. Now one start moving over the other with a certain relative velocity, let's call it u relative. Then in that case, absolutely one will be moving in forward direction, then the other will be moving in backward direction. Absolutely one will be moving in upward direction, the other will be moving in downward direction. Absolutely if one is moving towards u, then the other must be moving away from u so as to nullify the final momentum of the system, same as that of initial one. Initially system was at rest, so the linear momentum will also be equal to 0, right? So here can we say that velocity of one object with respect to ground finally in magnitude terms, that will be given by, if you want to write the velocity of the first object, then in numerator the mass of the second object will be coming, which means velocity of one with respect to ground, that will be equal to mass of the second one, mass of the other one, m2 into u relative over m1 plus m2. And in similar fashion, velocity of 2 with respect to ground will be given by the magnitude 1. m1, the other mass, velocity of second will be equal to the other mass m1 into u relative over m1 plus m2. m1 plus m2. Is it fine? The shortcut? Another thing is, if initially the two-particle system is at rest and one starts moving towards forward direction, the other must be moving in the opposite sense, which means the direction of velocity of one with respect to ground, not necessarily ground, with respect to any other frame of reference, its direction, the direction, which means unit vector, that will be negative of velocity of second with respect to any other frame of reference. So that is direction, unit vector. Hope you'll remember it, because the two-particle system is one of the most common and important systems in physics. So you are going to remember it, right, as a shortcut.